All right, let's talk about our final topic in equilibrium, which is the equilibrium constant for the solubility product, or what we call Ksp. And what this is this tells us essentially at equilibrium an partially soluble or a solution that has something dissolved in it. It lets us know how much is dissolved and if any has precipitated or will be a precipitate sitting at the bottom when it reaches equilibrium. So since we're going to talk about solubility, let's review real quick what a saturated solution is from our solutions unit. So if we look at an unsaturated solution, what does that mean? Well, an unsaturated solution, there's still room in the solution for more of our solid solute to dissolve. And so what we can see depicted here is that our solid is dissolving into the aqueous state, and it will continue to do that until we hit saturation, until there's no more room. So once it's saturated, what's going to happen is that here's our equilibrium. Notice the two different sided arrows. While some solids continue to dissolve, others are reprecipitating into the solid. So at equilibrium in a saturated solution, there's this constant back and forth of particles dissolving and particles re-solidifying into a precipitate, such that when we look at it, we don't see a change. What we see is a saturated solution with a pile of precipitate sitting at the bottom, but we constantly have this exchange of particles happening between the two states. So at that point, our solution is saturated. So what we can do is we can talk about our solubility product as a constant. We can describe what that's going to look like. So our Ksp describes the equilibrium of a saturated solution. If we describe our saturated solution as the following reaction: some solid in equilibrium with its cation, and we need to make note if there's any coefficient, which is aqueous, and the anion, again, if there's any coefficient, and that is aqueous as well. That means that our solubility product expression, our Ksp, will always be written as the cation times the anion. Why is there nothing on bottom? Because our reactant is a solid. Solids and liquids never impact our equilibrium expressions. They don't have a meaningful impact on that value. So they're always going to follow this pattern. What we want to do is make sense of this number. What does it mean when you calculate the constant? Well, if you get a large value, something greater than 1 for your Ksp, that means that this substance is very soluble. Or another way of saying that is that a lot of this substance will dissolve into the solution. So you're going to have little to no precipitate sitting at the bottom at equilibrium. If your Ksp is small, something less than 1, that tells us that not a lot will dissolve. And that means that at saturation, at equilibrium, you are going to see very quickly an excess of solid build up. So what does this look like in application? Well, we can do a calculation if we want to find the equilibrium constant of a saturated solution of aluminum chloride. Let's remember how we write formulas from our names. So this is ionic, it's a metal and a non-metal. Aluminum as an ion has a +3 charge. Chloride as an ion has a -1. We can use crisscross to come up with the formula. This is Al1Cl3. So we use crisscross to get our subscripts. And our molar solubility, that's our change, is 5.5 times 10 to the -4th molar. So we're going to do a race table. So reaction, initial concentrations, change in concentration, and equilibrium concentration. Our reaction follows that pattern we saw on the last slide. Our solid aluminum chloride in a reversible reaction with its cation, aluminum, and chloride. And we need to make sure we balance this. 1 aluminum, 3 chlorines, 3 chlorines. going to fill in our rice table. What do we know? Well, the initial concentration of our solid doesn't matter. Equilibrium concentration doesn't matter. It's a solid. We don't have any product yet. Our molar solubility is our change. We're going to lose that much of our solid as it dissolves. And we're going to gain that product. And again, we're going to use the coefficients to establish our mole ratio. 1 AlCl3 for every 1 aluminum ion. So we're going to have plus 5.5 times 10 to the negative fourth molar. For every 1 aluminum chloride, there are 3 chloride ions. So we're going to take that 5.5 times 10 to the negative fourth and multiply it by 3, and we get 1.65 times 10 to the negative third. We're going to go through and find our equilibrium amount. So 0 plus 5.5 times 10 to the negative fourth is 5.5 times 10 to the negative fourth, and 0 plus 1.65 times 10 to the negative third is just that. So our goal with this was to get our equilibrium concentrations of our ions. Our Ksp is going to be the concentration of the products. Our reactants are solid or liquid, so they don't count. So we have aluminum ion times chloride ion cubed because of the coefficient. Plug in what we know, 5.5 times 10 to the negative fourth times 1.65 times 10 to the negative third cubed. Plug that in on our calculator, and we get a Ksp of 2.47 times 10 to the negative 12. Or in other words, 0.0000000000247. That is very small. What does that tell us? This is not very soluble. So not a lot of aluminum chloride is going to dissolve in water at equilibrium. It'll form a saturated solution very quickly. Very little will saturate very quickly. All right, so let's look at another example. In this one, we want to determine the molar solubility. So we're given the equilibrium constant, and we're told the nature of our saturated solution, and we're going to solve for the molar solubility. So first thing, let's write our reaction. We need to know how to write calcium hydroxide. Calcium is a group 2 metal, so it has a charge of +2. Hydroxide is one of our polyatomics, that is OH with a -1 charge. I'm going to use crisscross. I always put parentheses around my polyatomics. That way I know that any subscript goes on the outside. It's going to have a subscript of 2. The calcium will have a subscript of 1. So calcium hydroxide, solid, in a reversible reaction with its ions, which are a calcium +2, which is aqueous, and hydroxide, which is aqueous. Let's balance. 1 calcium, 2 hydroxides, 2 hydroxides. Now let's fill in the rest of our table, the initial, the change, and the equilibrium. So here, again, I don't care what the initial concentration is of our solid, nor do I care about the equilibrium because it's a solid. We know that that doesn't impact. We start out with no dissolved ions, and we end up with dissolved ions at the end. How is this going to change? Well, we don't know yet. That's what we're trying to figure out. But we know we're going to lose X amount of calcium hydroxide, and we're going to gain in a 1-to-1 ratio X amount of calcium ion, and in a 1-to-2 ratio, 2X amount of the hydroxide. 0 plus X is X. 0 plus 2X is 2X. So what do we do from here? Well, we still know how to write our expression. That is the calcium ion concentration times the hydroxide ion concentration squared. We know the value of Ksp, that is 2.0 times 10 to the negative 8 is equal to, and we can plug in x for calcium and 2x squared for hydroxide, and we can start solving for x. So 2 times 10 to the negative 8 is equal to x times 2 squared is 4, x squared is x squared. Now I get 2 times 10 to the negative 8 is equal to 4x squared times x is 4x cubed. I can divide both sides by 4. I get 5 times 10 to the negative 9th is equal to x cubed. I can take the cube root of each side. So I get x by itself. And I get that x is equal to 1.7 times 10 to the negative 3rd molar. We need to have a unit on this. This is the molar solubility. It's not our equilibrium expression. It is our molar solubility, or in other words, this tells us what our change is. We're going to lose 1.7 times 10 to the negative 3rd molar of the solid, and we're going to gain 1.7 times 10 to the negative 3rd molar of the calcium ion, and twice this of the hydroxide ion. All right, so to finish up today, what I'd like you to do is to try one of these on your own. You know the drill at this point. Go ahead and pause the video. Attempt to determine the molar solubility, so just like our last example, of a saturated solution of aluminum chloride given the equilibrium constant. When you're done solving that, go ahead and unpause the video and we'll go through the answer here. All right, so I'm going to set up my rice table. My reaction is aluminum chloride, AlCl3, solid, yields in a reversible reaction, aluminum ions and chloride ions, and I've balanced that. Filling in my chart. Not interested in the initial or equilibrium of my solid, starting with no dissolved ions. Our change, we're going to lose some amount of solid, and we're going to gain X amount of aluminum ions and 3X amount of chloride ions. That means that our equilibrium is X and 3X. Our equilibrium expression is the concentration of the aluminum ion times the concentration of the chloride ion cubed. Plug in what we know. We know the value of Ksp is 2.47 times 10 to the negative 12 equals x times 3x cubed. And then we're going to start solving for x. And so that's going to be, 3 cubed is 27, x cubed, and then x times x cubed, we have 27, x raised to the 4th. Divide both sides by 27. I get x to the 4th is equal to 9.15 times 10 to the negative 14th. Take the 4th root of both sides. And I get x is equal to 5.5 times 10 to the negative 4th molar. And this was the molar solubility that we had in the first problem that we did in these notes. And it's a great check that I did this correctly. All right, go ahead and move on to worksheet 11.5 to get more practice on this. On Friday, I will post the answer key. Have a wonderful day, and thanks for tuning into chemistry.